All right, hello everyone. I am Landon. Oh, let me get the annotation. And this is Smith's 181 review. And this is for exam 2. All right, so this is not your review. This was all I was given. I wasn't given any material for your course, but I hope this is somewhat similar. Yeah, so let's jump into it. Okay, so start with, perhaps we'll start with problem 1. Looks like we're doing some derivatives. And we're asked to compute this here. Okay, all right, so we have a quotient, right? We have two functions, f of x over g of x. All right, so let's first identify what those are. So we have f of x equal to e of x, and then we have g of x equal to 2 minus x to the fourth, right? Okay, so if we want to find the derivative, dx of f of x over g of x, there's a formula for it, right? That's going to be something like, if I remember correctly, it's g of x times the derivative of f, so f prime, minus, let's see, that should be g prime of x, and then times f of x, all over the bottom function squared, so g of x squared, right? Okay, so that's the derivative. Yeah, all right, so now let's compute it. All right, so we're going to find the derivatives of each of these and then just plug it into this formula, right? So f prime of x, what is that? Well, it's just e to the x. E to the x isn't affected by a derivative, right? It just does nothing. So we're left with itself. All right, now g of x. So g of x is a little more complicated. So we have to do these two terms. So what we do here, 2 minus x to the fourth. So we can break this up amongst the two terms. So d dx of 2 minus d dx of x to the fourth, right? So this is the derivative of a constant. The derivative of any constant is just 0. So we have 0 there. And then minus the other one, we have x to a power. We can use the power rule. Okay, so remember the power rule. It ends up going something like this. We bring down the power 4, and then we subtract 1 from the power we had there. So it's going to be x to the 4 minus 1, or rather just 3, right? So we can get rid of the 0 because, well, it's just 0, right? So minus 4x to the power of 3. And that's what we get for the derivative there. Okay, so now we're going to plug it into everything. So the derivative of e to the x over 2 minus x to the fourth, that is going to be g of x. G of x is just 2 minus x to the fourth. Do be sure to put parentheses here. Otherwise, things will start getting a bit messed up because we're going to multiply with this other term. All right, and now the derivative of f, which is just e to the x, minus g prime. G prime, we found, is negative 4x to the power 3. And now we multiply it by f. F is going to be, again, e to the x. And lastly, we have g, just ordinary g, to the power of 2. So it's going to be 2 minus x to the fourth squared. All right. Okay, so now we're basically done. We just have to clean it up a bit more, right? All right, so how about let's see, there's a couple different ways we can go about it. I think what I'll do is I'll distribute the e into here. And there's technically distribution here, but it's just one term, right? Two terms being multiplied by one another. Let's clean up the negatives, though. And that way, it's a bit easier to remove those parentheses. And now, let's see, what do we get? So we get 2 e to the x minus x to the fourth e to the x plus 4x to the third e to the x. Something like that, right? Okay, let's see if we can clean that up at all anymore. And yeah, I'm not sure if we can. I think that's pretty much simplified. So, and of course we have the denominator squared. And I'd say that's a pretty suitable answer. And let's box it. And there we are. That appears to be the answer for that. Yeah, I will likely be making a lot of mistakes in this. So yeah, be sure to correct me when going about this. Yeah, okay, so let's move on. Let's try the second problem. Okay, I'm going to erase all the work now. Okay, and now we want to find not only the first, but also the second derivative of this new function, x to the ninth natural log of x. All right, so let's set it up. So we have the derivative of x to the ninth ln x. Okay, so remember when going through all of these, all the rules, we want to peel away the outer layers first. So I see this, and maybe you'd want to do power rule, right? So you don't want to do power rule just yet because the outer layer here is multiplication. So you want to get rid of that outer layer and then get into the inner ones. It's kind of the opposite of the order of operations. So there's a power here. You'd maybe want to do the power first, but in this case, you don't want to do that just yet because we have to deal with the multiplication first. Okay, so let's use the product rule. So product rule allows us to take apart products, right? So let's do that. Product rule says that if you have f of x times g of x, that this is equal to f of x times g prime of x plus f prime of x times g of x. So the way I like to remember it is left d right plus right d left. Oops, I think I may have wrote it in the opposite order, but nonetheless, it works because we can just swap these two terms if needed. But anyway, yeah, so you're basically going to have these two terms. One of them is going to have the derivative. The other one is not going to be a derivative. And similar with this one, we just swap them, right? So that's kind of how I remember it. All right, so let's apply it. So set f of x equal to x to the ninth. That's a horrible 9. Let me make that a little better. And then g of x, I'll set equal to the natural log. All right, so this is where we're at so far. We want to apply this formula. We have to find the derivatives first, right? All right, so f prime of x. This is now when we're going to use the power rule, right? So we have x to the ninth. We want to bring down the power, subtract 1 from the power in the power place, if you know what I mean. So it would be like 9 minus 1 right here. So in the power, we're going to subtract 1. And that I'll just erase and simplify immediately. That's just 8, right? Okay, and now the natural log. Okay, so this one is one you just have to remember. This one is a bit, it's difficult to figure out on your own. So yeah, it's worth remembering that the derivative of the natural log is just 1 over x. All right, so now that we know that, we can plug everything in. So now the derivative of x to the ninth ln x, this is equal to f, which is just x to the ninth, and then we have g prime. G prime is this times 1 over x. Now for the second term, f prime, which is 9x to the 8 times g of x, right? G of x is just ln of x. Okay, so we have the first derivative. Let's clean it up a bit. This is going to cancel out with one of the powers, so it's going to be an 8. And then we're left with x to the 8 plus 9x to the 8 ln x. You could factor it out if you wanted. That would be something like x to the 8, 1 plus 9 ln x. But it doesn't really matter. Either of these, I would say, are perfectly fine. And there we are. So that is the first part. Okay, so as the problem notates, that's f prime. So let me write that down here. And actually, let me write it in the second form. I'll explain why I'm doing that in just a moment. So x to the 8, 9x to the 8 ln x. Okay, sorry, my handwriting is quite horrible, but I think you guys know what's going on. Okay, so now we want to do the, whoops, not that one, this one. We want to do the second derivative. So we're going to repeat the process and get our answer. All right, so now I'm going to erase everything here. We're going to repeat the same exact thing. Okay, so now we want to find the derivative of x to the 8, 9x to the 8 ln x. Okay, so we want to do the opposite of PEMDAS. We want to do addition. So we're going to use the addition rule, right? So that's just going to find us, or rather give us the this right here. All right, so we have that, and now we just apply our rules. So derivative of x to the 8 is going to be 8x to the 7th, right? Subtract 1. And now the other one, we have to use the product rule again. Okay, so I'm going to consider this. Here, let me change colors. This would be our first function. This will be our second one. Okay, so I'm going to do this without writing out the rule. I'm just going to go straight into it. So it's going to be the derivative of the first one, or the second one. It depends on your order. It doesn't matter too much. And then it's going to be times ln of x. And then we're going to add the other one. That's going to be the 9x to the 8 times the derivative of ln of x, right? Just like that. Okay, and now let's figure that out. This term stays the same. Take the derivative of this. It's going to be multiplied by this, don't forget. And then that is going to be, let's see, 8 times 9, is that, oh gosh, is that 56? Okay, let's just say it's 56. You guys can double check me in the calculator. So that's going to be 56, and then that's going to be x to the 7th. And do recall that this is 9 times 8. I brought down the power, and I multiplied the two. Okay, and then we still have our ln x at the end, because this is one large term, right? And now we have our last bit. 9x to the 8 stays the same, but we take the derivative of this. That's just 1 over x. But we can simplify this further. So we have power 1 here and 8. They cancel, and you just have a 7, right? So here, let me just do that all in one statement. And we have a 7 right there. Okay, so we're almost done. We can combine like terms a little bit. 9 plus 8, I think that's 17. And there we are. Okay. All right, so that seems to be f double prime of x. And yeah, that's about it. Okay, so let's move on to the next problem. I'm going to clear all the work. Okay, so here, let's see. Let's try this one. Okay, so we want to find the first derivative of sine of x times secant of x squared. Okay. So we have a product here, and we also have a lot of other stuff going on. First of all, these are trig functions, and then we have something inside of another function, right? So we have composition of functions. So that calls for chain rule, right? So maybe not immediately, but we're going to have to use chain rule at some point. Okay, so let's start with the outer layer. The outer layer is the product. Okay, so let's start with the product. So here, let me do this up top. Derivative of sine of x multiplied by secant of x squared. That's going to be the left times the derivative of the right. Sine of x times dx of secant of x squared. And then plus the other term. So that's going to be the derivative of sine of x times secant of x squared. Okay, so let's try to figure this out. Okay, let's start with maybe the tough one. So secant of x squared. So first off, we need to figure out what the derivative of secant is, right? Okay, so let's see if we can recall what that is. Okay, I was having trouble remembering myself. So it looks to be, or maybe I'll just write this elsewhere. So the derivative of secant of x is equal to tangent of x times secant of x. So we just end up tacking on a tangent right there as well. Okay. All right, so how do we do this with chain rule? So recall, chain rule says that the derivative of f of g of x, let's see, I need one more parenthesis, that this is going to be f prime of g of x times g prime of x. Okay, so let's try to understand this. Whatever f is, we are taking the derivative of it and then putting g of x into it. And then we have to deal with g of x. So what we do is take the derivative of that and then just plop it right next to this term right here. So just multiplying them, right? Okay, so I like to think of it as, again, you're trying to do the outer layer. You'll peel away the outer layer by taking the derivative of this, and then you deal with the inner layer by tacking on this guy right here. All right, so let's figure out what we have here. What is our outer and what is our inner? Well, I see our outer layer is secant and our inner is the square function, just x squared, right? So let's set that up. F of x is equal to secant of x. G of x is equal to x squared. All right, so let's figure out their derivatives. We actually already know what f prime of x is. That's, tangent of x, secant of x. And then g prime, we know that. That's just going to be 2x, right? So it'd be 2 minus 1, but that's just 1, right? So we can just imagine there's an invisible 1 right there. Okay, all right, so now for this first term, it's going to be sine of x multiplied by this whole thing. And we're just going to plug in f of x and g of x, right? Okay, so I'm going to put parentheses around that just to kind of distinguish it from the sine of x. So f prime, that is this right here. We have to put g of x into it. So let's first do that before we start writing out the whole thing. So f prime of x, or rather, f prime of g of x, we're going to plug in g of x everywhere we saw x. So that's going to be tangent of g of x times secant of g of x. All right, and now g of x is just 2x, so we can just replace every g of x with 2x. Okay, so let's actually just do that in one go. Okay, so we put in 2x right there, 2x right there, and boom, we got it. All right, so now let's fill this in. We have tangent of 2x, secant of 2x. Oh, oops. I think I may have mixed it up. I apologize. Yeah, so don't make the mistake I did. I just plugged in g prime of x, which is incorrect. We're plugging in g of x, not g prime. Okay, so let me fix that real quick. So remember the formula, it goes f prime of x of g of x, not g prime. So yeah. Okay, so that's just going to be an x squared right there and an x squared right there. And let's fix that right here. All right, x squared, x squared. All right, and now, oops, I apologize if that was slow. Now we're going to deal with the derivative, right? So we're going to multiply by the derivative g prime of x, which is 2x. And there we're done with that term. Now we'll deal with the second term. So the second term is the derivative of sine of x. So remember, the derivative of sine of x is just cosine, right? So we have cosine of x, secant of x squared. And there's our answer, this whole thing. And yeah, you can try to clean it up a little bit. Let's see, there's not much that can be done with this. And there's not much that can be done with it. You could, for instance, get rid of the parentheses and move this 2x up front. I think that's a little prettier, but other than that, there's not much else that can be done. And yeah, there we are. Okay, all right, so let's move on to the next one. Okay, so maybe we'll just do a couple more of these and move on. Okay, so let's do perhaps this next one, then maybe we'll move on to a different flavor of problems. All right, so this one's pretty tricky. It's asking us to find the 33rd derivative of this function. Okay, so one way of doing this is we could just try to run through the derivative 33 times, and that's pretty rough, that's pretty time consuming. So let's go about it maybe more strategically. So, and also I do want to emphasize that they can actually just change this number arbitrarily. They can make this like 1001 or something random like that. So obviously there's no way you can do 1001 derivatives in one exam. So yeah, like I said, we want to do something a bit more careful. So let's notice one behavior about this function. Let's take a couple derivatives of it. Not all of them, of course, just a couple. So let's do y is cosine of x. So that you can kind of think of as the 0th derivative. It's kind of like y of 0 right there. Doesn't really make sense, but yeah, kind of. I don't know. It's up to interpretation, I suppose. So now let's do the first derivative. So remember, it's just another thing you have to remember. The derivative of cosine is negative sine. All right, and let's do it again. Take the second derivative. So now we take the derivative of sine. There's a constant up front. There's a -1 in front of it. So what we're going to do is just kind of ignore it, just kind of pull it out, right? So derivative negative sine of x is just going to be negative d dx of sine of x. So that's the constant property, or the coefficient property, where you can just pull them out. And now we just apply our ordinary rules. Sine of x is cosine of x, right? So negative cosine of x, because we still have negative up front. And let's do it again. Y triple prime that is going to be, you can feel free to double check me, that should be sine of x, because the derivative of this is negative sine, but we have a negative up front already. The negatives cancel, and then we're just left with sine of x. All right, and now we're going to do it just one more time. So if you perhaps entertain my poor notation, I'll do y4 prime. This probably is better off by notating like that. Yeah, so let's take the derivative of sine. That is, again, cosine of x. So let's try to find some nice behavior, what's going on. If we were to take the derivative of this again, and we were to do the fifth derivative, it's just going to be negative sine of x, exactly the same as this. So we keep going through the same behavior. There's some names for this. It sometimes is called a cyclic behavior or even a periodic behavior. It just means that it's going to keep repeating forever and ever these same four derivatives. So what we need to do is figure out, is the 33rd, which one is it going to land on? Is it going to land on this one, this one, this one, or this one, right? It's not going to be any other. So let's try to line this up. This is the 0th, this is the first, second, third. And this one right here, perhaps I'll change colors. This is the 4th, 5th, and then there'd be the 6th, and then 7th. So this would be negative cosine of x and then sine of x. Okay, notice how it keeps repeating multiples of 4. So all of these ones are multiples of 4. You can double check me that the 8th derivative, y to the 8th, is also going to be cosine of x. And then it'll keep going like this. So these are all multiples of 8. These are just one-off multiples of 8. They're just one above multiple of 8. 5 is 1 plus a multiple of 4. Sorry, did I keep saying multiple of 8? I meant multiple of 4. So yeah, this one is a 1 above a multiple of 4, namely 0. 0 is a multiple of everything, right? And then this one is 1 above 4. 9 is 1 above 8, so forth, etc. All right, so what I'm trying to illustrate is that we have to figure out what's the remainder of 33. So if we can find the remainder of it, then that's going to be one of these numbers, and that'll be the derivative. All right, so 33, let's see, let me see if I can recall my multiples of 4. So I know 28 is a multiple of 4. That is 28 is 7 times 4, right? We actually don't care about the 7. We just want to know that it's a multiple of 4, right? Okay, so let's count up to 33. So we have 28, 29, 30, 31, 32, 33. Okay, so this is 0, 1, 2, 3, 4, and then 1. So I'm counting up to, or rather, this should be a 0 again. It can be a 4, but we are counting across these. So what this is saying is that the y to the 28th is equal to cosine of x, because it's a multiple of 4. And then we keep counting, and we see that 32 is also a multiple of 4. So then that is also cosine of x. Finally, finally, we see that 33 lands in the one right after. Hence, our answer is that right there, negative sine of x. And we're done. So yeah, that was a pretty tricky one, but there's a lot of problems like these where you want to try to find the behavior in them. And yeah, this can be a bit time consuming, but try to do something like that. See if you can find a pattern over the derivatives. And you can do that just by trying a couple. See if you can find the pattern. Yeah, that's about it. Yeah, okay, I'm going to clear the work. I have seen problems similar to these where they actually ask you to do the same thing. That one is a lot harder, But yeah, maybe you can give a couple tries in that one if you want to see like kind of how it ends up going with that one. But yeah, I've seen that on some exams where they ask you to find the, I don't know, maybe the 9th derivative of something like that. But yeah, that I would say that's an extreme problem they may ask you. All right, so let's maybe move on to some other types of problems. So we have a lot more derivatives here. Just kind of scroll by them if anyone wants to give them a try. Okay, we got some limits. Let's try these. Okay, so we have the limit as x approaches 0 of this function here. Sine of 3x, tangent of 7x. All right, so remember in this chapter, or this kind of area in the book, we learned how to do derivatives, and we learned how limits allow us to get to derivatives. And now we're doing the opposite, right? We're showing how derivatives can actually help limits. So we do that through L'Hopital's rule, right? Maybe this is an example of L'Hopital. So let's see if the criteria is met. So first thing you want to do with limit is try to see if you can plug it in. Try to see if you can just plug in x equals 0 and if it works out. So what would happen in that case? So we have sine of 3 times 0, that's just 0, right? Over tangent of 7 times 0, but again, that's just 0. Okay, so let's compute this. Sine of 0 is just 0. Tangent of 0 is also just 0. So we have an issue now. We have 0 over 0. It's not really a number, right? So recall, if you have something over 0, then you may be able to figure out the limit. Maybe it's infinity or something like that. But when you have 0 over 0, you have to do something else. So this calls for L'Hopital's rule. So limit as x approaches 0 of sine of 3x over tangent, of, where do I keep writing 3? 7x has the, I like to write this notation, form 0 over 0. So that calls for L'Hopital's rule because it's in that form. The only other case where you can use L'Hopital's rule is when you have infinity over infinity. They could be plus minus, of course, it doesn't matter, but as long as it's infinity over 0, or that's completely wrong. Infinity over infinity or 0 over 0. If you have something like this, or even, not that last one, but something like this, I'm pretty sure this last one is also indeterminate. Anything like that, you cannot use L'Hopital's rule, right? It has to be this or this. So yeah, just something to keep in mind. You can modify these though to get into something like this though. That is something you can do. All right, so L'Hopital's rule, let's apply it. So it's nice to keep a note. I like to do something like this, like, yeah, this is kind of like the first few letters of L'Hopital. I believe it's notated like that, but it's nice to do that for your professor so it's easier for them to follow your work. Regardless, let's apply it. So it's going to be the derivative of the top over the derivative of the bottom. Okay, so we have a function within a function. Namely, we have 3x inside of the sine function. So that calls for chain rule. So we still have the limit, don't forget it, of sine of x, or sine of 3x. So, sorry, I don't know where my head's at. We take the derivative of the outside, right? So it's going to be cosine, leave the inside the same, and now we're going to multiply by the derivative of the inside, which is 3x. The inside is 3x. So the derivative is going to be 3. So now we're going to multiply by 3, and we get this. We do the same thing for the bottom. So you should end up getting, I believe, it's this right here. So the derivative of tangent is, that ends up being secant squared. And then we have the inside argument, which is 7x. Just kind of replace this with a 7, right? And our result ends up being 7. So we multiply by right there. So yeah, just another thing to remember, at least if I'm recalling it correctly. Sorry, I have trouble remembering some of the derivatives. Pretty sure it's secant squared of x. All right, so now let's try it again. Let's see if this was helpful in any way. So now if we were to plug in 0 here, so we would end up getting, perhaps I'll do it in the top right corner, 3 times cosine of 0 over 7 times secant squared of 0. So cosine of 0 is just 1. Secant squared of 0 is, let's see, what is that? I'm pretty sure there's an issue with that too, because I'm pretty sure this is undefined. So let's see if we can change this a little bit. What do we know about secant? Secant, remember our trig, secant of x is equal to 1 over cosine of x, right? Well, we have a cosine here and a cosine here. Well, let's see. Does that help us at all? Actually, whoops. I think I think I'm recalling this incorrectly. I apologize. I believe what I'm thinking of is cosecant. Yeah, cosecant of 0 is undefined. Yeah, I apologize. I'm pretty sure this is so good because if we were to plug in cosine of 0, so what we have is secant of 0, which is 1 over cosine is 0, but cosine of 0 we just said is 1. So I apologize. Yeah, that's just 1. So yeah, okay, sweet. We actually have no issues. That would have been quite cumbersome. All right, so this is also just 1 because we have secant squared of, yeah, we just have secant squared of 0. So that ends up being secant of 0 squared. This is 1. 1 squared is just 1. Boom. All right, perfect. Okay, so now finally, we end up getting to our answer, which is just what's left over. 3 over 7. And there we are. Okay, so yeah, that was quite a bit. Let's go over that one more time. First, try to plug in your value. If you can plug it in and there's no issue, you're good. That'll be your answer. If not, if you get something like 0 over 0 or infinity over infinity, try to use L'Hopital's rule. So L'Hopital's rule says that you take derivative of the top and the bottom. And then once you do that, try to see if it works out again. See if you can plug in 0 again, or whatever your value is. So then, in our case, we found that it actually works out very nicely. Ends up, when we plug it in, this turns to 1. This also turns to 1. And all we're left with is 3 over 7. That's our answer. And there we are. Okay, so let's try, maybe we'll try to quickly go through one more. And then I'd like to get to some related rates problems. So those are the real tricky ones, I think. Yeah, all right, so let me clear this work and we'll do this next one. Okay, so this next one is all right over here on the left. Limit as x approaches 0, sine cubed of 2x over x cubed. Okay, so as always, plug in the value, see if it works out. Okay, you plug in 0 into here, you're going to get 0. Sine of 0 is equal to 0. And if you plug in 0 into here, you're just going to get 0. So in short, we get 0 over 0. Apply L'Hopital's rule, right? Okay, so let's run through that. Take the derivative. So limit as x approaches 0, d dx of sine cubed 2x over d dx of x cubed. Okay, and do note this is form 0 over 0. Okay, so let's give this a go. Oops, not h, x. Okay, so derivative of the top. The outer layer is the power, right? So we have to do the power first. So we do chain rule. We do the derivative of the outside. That's going to be 3. Bring it down. And then we're going to subtract 1 from it. So it's going to be sine of 2. And then the argument is 2x. Okay, so we're not done yet. We still have to apply chain rule. That was the outermost layer. Now the next layer is going to be the sine of x. So now we have the derivative of sine of 2x. Okay, so let's actually do that on the side. So that is going to be cosine, right? Yeah, cosine. We leave the inside alone still. We're applying chain rule again. And now we take the derivative of the inside. Derivative of 2x is just going to be 2. So there's going to be 2 right there. Okay, so does that make sense? So we applied 2 chain rules. 1 for the cubed. So we have something cubed. And then the next one was the sine of 2x. So we brought down to 3, got rid of that, and then we were left with 2. And that's what we have right here. Then we multiply by the derivative of the inside, which is the derivative of this. That's the inner function. Then to take the derivative of this, it ends up being the derivative of the outside, the cosine, or the derivative of the sine rather, and that results in cosine. And then we multiply by the derivative of the inside, which is 2. Okay. All right, so where does this take us? Here, let me get rid of all of this. So remember, this just resulted. Let me put parentheses around this. Multiplied by 2 cosine 2x, right? Okay, so now derivative of the bottom, that's not too bad. It's just power rule, 3x squared. Okay, so we can clean this up a bit, cancel that with that. And I think that's about it. Let me write this a bit neater. So we have sine squared of 2x cosine 2x. And there's a 2 up front still, right? This 2 right here. And then x squared. Okay, so let's see. Is this any better? So this one actually, let's plug in 0 again. So we plug in 0. This ends up being, this right here is 0. So then the whole thing becomes 0, right? And then that means even more so, the entire numerator is 0. And this one ends up being 0 as well. So we're back at the same place. We have to use Hopital's rule again. Okay, so let's go through that. So this ends up being the limit as x approaches 0 of the derivative of the top. So while I'm at it, I'm actually going to bring this 2 out. So I'm going to bring this 2 out so we don't have to worry about it whatsoever. So let me scoot this equal sign over. 2 times the limit of everything. Okay, so we have derivative of this numerator. Let me actually write out the derivative of the bottom first. That's just going to be 2x, right? Bring down the 2, subtract 1 from the power. And look at that, that actually cancels with that, which is quite nice. We can just bring that 2 out of the limit and have it cancel with that. Okay, so now we have to find the derivative. Here, I'll do that down here. Of sine squared of 2x multiplied by cosine of 2x. Again, power rule, right? That's the outermost layer. Let's deal with that. So that's going to be sine squared of 2x multiplied by the derivative cosine 2x plus the derivative of sine squared 2x, right? Cosine 2x. Okay, Let's start with this one. Chain rule again. Minus sign, that's the outer one, multiplied by 2, or sorry, inside the function is going to be 2x still. Now we have to multiply by 2. So I'm going to multiply that on the left right there. Oops. Minus 2 right there. Okay, perfect. Now we do this one. Chain rule, again, we have to do multiple. So we bring down the 2 because the power is the outermost function. 2 sine of 2x. Now we do the derivative of sine of 2x. That's the inner one. So just scratch out the power, that's the inner function. This is going to be cosine, right? Cosine of 2x, we keep the inside the same. Now multiply by 2, the derivative of 2x, which is just 2. Okay, so these two are being multiplied. These are multiplied together. These two, that is. These two are multiplied. And let's bring everything together. So the first term, minus 2, we have a sine of 2x, and then we have the same thing squared. They're being multiplied. We can bring them together to be 1 power. Sine 3, oops, 2x, just like that. Okay, that first term isn't too bad. Now the second one, we have these two terms being multiplied and also being multiplied by this. So remember, this whole thing turned into this whole monstrosity over here. All right, so that's going to be 4 up front. 2 times 2, that's 4. Then we have a sine of 2x. Let me put parentheses around that. And then we have a cosine 2x times cosine 2x. Let me combine those into one thing. Cosine squared of 2x. All right, so quite a lot going on. Let's remember where we were. So this is the derivative of this right here. Let's plug it in. So it's minus 2 sine cubed of 2x plus 4 sine of 2x cosine squared of 2x. Damn. We end up actually getting back to the same place again, which is quite unfortunate. So yeah, this one is a long one. We can see that if you plug in 0 again, this term will be 0. This term will be 0. And so this whole thing right there is going to be 0. Again, numerator 0. And you can check the denominator will also be 0. And hence L'Hopital again. Oh, man, we're almost there, all right? So just one more apply and we'll get there. And the reason I know that is because the derivative of x is going to be 1. So we're guaranteed that we won't have a 0 in the denominator. Okay, let's run through that, and then we should be done. All right, let me remove all this on the bottom. So form, again, 0 over 0. So this is our last attempt of L'Hopital. Okay, so limit as x approaches 0 of the derivative of the bottom is just going to be 1. So the 1 at the bottom. And let's figure out the numerator. So the numerator is actually going to be our answer. So if we can figure out that, we're good. Okay. And the reason it's going to be our answer is because this is just a 1, right? You divide anything by 1, you're going to get the same thing. All right, so negative 2 sine cubed of 2x plus 4 sine of 2x cosine squared of 2x. Okay, so let's run through this. All right, I'm going to go a little fast with this one. Minus 2 times 3 sine of sine squared of 2x, and then we're going to multiply, so let me put parentheses around that, multiply by the derivative of the inside, which is going to be the derivative of sine. That's going to be cosine of 2x, multiplied by the derivative of the inside there, which is 2x, so the derivative gives us 2. So multiply 2 right there. So let me clean this up a little bit. Let me multiply everything. Minus, let's see, 2 times 3 times 2. That's 4 times 3, that's 12. Sine squared of 2x times cosine 2x. Okay, so that's the first term. Second term, there's going to be quite a lot going on here because we have a power rule. We have the product of two functions. So let's do that next. All right, so this is going to be our first function. This is going to be our second. So here, let me, 4 sine of 2x times the derivative cosine squared of 2x plus derivative of 4 sine 2x. Let me try to see if I can squeeze this in. Cosine squared of 2x. Okay. All right, so this is 2. There's going to be another 2 from that chain rule, so I'm kind of skipping ahead. So it's going to be 4 cosine of 2x times sine of 2x. So what I'm doing is bringing down the 2, bringing the 2 up front, and then I'm taking the derivative of the outside. The derivative of the outside, which is the power function. We leave the inside the same. And then we're going to multiply by the derivative of the cosine 2x, which is just sine 2x. Again, chain rule, just as before, there's an extra 2 from that, and that's why we have a 4 up front. Okay, now this last term is going to be, this is just going to be cosine 2x, and then we have an extra 2 from the chain rule. So 4 times 2, it's going to be 8. And then we have this over, and also this is a product of this. Okay, so this should be it. Let's put this all together. And while we're at it, let's just plug in 0 into everything, because that's what our answer will be, where we plug in 0 into everything. So if there's a sign anywhere, whole thing's going to be 0. So our first term is this one. There's a sign. This is going to be 0. Sine of 0 is 0. So boom, 0. All right, next term. We have a sign in our second term. We actually have 2 of them. So then this whole term, 0. And lastly, we have no sign in this last one. Let's clean it up a little bit. It's 8 cosine. We have a squared and to the first power, so that's power 3 2x. Oh, we're almost there. All right, so now we just have to plug in 0 to this bit. This is going to be 0. Cosine of 0 is 1. And this whole term turns to be 1. And finally, our answer is 8. There we are. All right, so that one was quite a bit to deal with. Didn't really look like it, right? Okay, so that's the procedure for it. So yeah, let's move on. All right, so I'm going to skip the implicit differentiation for right now because I want to get to related rates. And if we have time, we'll get back to these ones, okay? And also logarithmic differentiation. Okay, so let's start with this one. This one is problem 5. Okay, so it says we have a cube increasing the size of the, the sides of the cube are increasing at a rate of 3 meters per second. At what rate is the volume of the cube increasing when the volume of the cube is this? Okay, so let's extract this information, put it in variables. That should be the first step. Okay, so we're working with the volume and side lengths. Let me draw a picture first. So we have some form of cube. So it's going to look something like this, right? All right, so it's a cube. That means all sides are going to be exactly the same. So I'm going to call it x. I'm just assigning a variable to each of these. So this length here is going to be same as this, because it's a cube. All right, so now the volume of the cube. Let's figure out a variable for that. So actually, let me bookkeep a bit. X is the side length of the cube. And now I'm going to define another variable, capital V. It'll be our volume. Oops, can't spell. Volume of cube. And let's figure out an expression of what that would be. So volume is going to be x times x times x, right? It's going to be the product of all three of these. So V is going to be x cubed, right? And now let's figure out our goal. Our goal is to figure out at what rate of the volume is the cube increasing. So they're asking what rate is the volume increasing. So when you hear rate increasing or decreasing, something like that, think derivative, right? So the volume is changing at some rate. That means the derivative, they want us to find the derivative of the volume. So find dv dt, and now I'm introducing a new variable, which is in respect to time. So let me write that right here. Time, and maybe this would be in respect to seconds. Okay, it doesn't really matter too much. It'll come into play later on of what the units are. Everything here appears to be meters except for this, sadly, which is in centimeters. So, all right, so they want us to find dv dt in respect to time when the volume of the cube is 125 centimeters cubed. Okay, so for simplicity, I'm just going to turn everything into centimeters because it'll make our life easier. So a 1 meter, so 3 meters is equal to 300 centimeters, right? So centa just means 100, so we just tack on 100 to it. Okay, it's important to get your units right, otherwise you're going to be off by a factor of 10 when listing your final answer. Okay, so how do we find dv dt? Well, we have this. Can we use it? Well, we want the derivative, so how can we introduce the derivative here? Well, let's just take the derivative. In respect to what? It could be in respect to x, but actually it's not what we want. We want the derivative in respect to time. So that's going to be t. So you can imagine both of these are variables of time. So x of t cubed, right? So that's how you can view them. Okay, so what that means is that when we take the derivative of both sides in respect to time, so we're taking the derivative of both sides. This is kind of implicit differentiation, the way I'm kind of writing it. It's the derivative of the left-hand side, derivative of the right-hand side. Whatever you do to one side, you must also do to the other. So in this case, we're taking derivative of both sides. Okay, so for simplicity, we don't really know what this is. In fact, we're looking for it. So let's just write it like this. Let's just kind of bring it up right there. And the reason I'm doing this is because, well, that's kind of how you can view it, right? It's another way of writing a derivative is you can just kind of bring it up right there if you wanted. It's quite poor notation sometimes, like if you're finding the derivative of like x squared, you could technically write it as dx squared dx, but that's just kind of clunky. So usually when there's a function, we put it like this, but if there's a variable, you can kind of just put it right there. That's just kind of convention, right? All right, so we have this, and now we take the derivative of this. So remember, x is a function of time. So that means we have chain rule here. So we do the outer layer, which is the power, bring down the power, we're left with the power squared, or rather the function squared. But we're not done because we have to take the derivative of the inner function, dx dt. We don't know what this is precisely, but maybe they give us more information. So how do we utilize this last bit they gave us? Each side of the cube is increasing at a rate of 3 meters per second. Well, that's precisely what we set x to be. The side length is increasing with time. Therefore, it tells us that dx dt is equal to, and recall that we're going to do it in this format, 300 centimeters per second. Perfect. So now we have this. Now we can plug it in, right? So yeah, so this gives us 3 times x squared times 300. I'm just going to drop the units for right now. So we're almost there. We almost solved for this, but not quite. We have to figure out what x is so we can plug it in. Okay, what other information did they tell us? Well, they told us this bit about the rate, 3 meters per second. They also told us when the volume is this. So we're solving for dv dt when this is true. Well, can we extract information from it? Well, remember we have this expression, right? We know v is equal to 125. So let's plug it in. So 125 for v is going to equal to x cubed. So we have to take the cube root of both sides to solve this, right? Cube root there, cube root there. These cancel, and we're just left with x on the right-hand side. So x is equal to the cube root of 125. So I think I happen to know this off the top of my head. You can plug this into a calculator. The cube root of 125, I'm pretty sure it's just 5. Perfect. That's exactly what we want. So now we plug it in. 3 times 5 squared times 300. All right, so this is our answer now. Let's plug it into a calculator. 3 times 5 squared times 300. That's quite a large number. I think it ends up being 22500. And we're almost done. We have to remember our units. So what are our units? So volume is in terms of units cubed, right? So it's units cubed, and our unit of length here is centimeters. So centimeters cubed, but this is a derivative, so we divide by what is on the bottom, and that unit is time. And specifically, that the unit of time is seconds. And there we are. We have our answer. Okay, yeah, so there's quite a lot going on there. So let's go through the general procedure one more time. So we're talking about the first thing you want to do, set up some variables that you think would be useful. Try to write down what you think they will be. It will be useful when it comes to bookkeeping. If you get lost or something, always reference your variables. All right, so next thing you want to do is write down your information. So the information in this case was the increasing at a rate 3 meters per second. That's this. Try to write it in terms of your variables. Often it'll be with derivatives, right? And then another thing you want to do is write your goal. So our goal here was to find this. We want to find dv dt when this is true. This is another bit of information you may want to use. In this case, we used it to solve for x. And yeah, and then you put it all together, you get your expression. Try to relate the variables in respect to one another. In this case, the volume was equal to x cubed. And then we want to get closer to our answer, a derivative. Therefore, we take the derivative in respect to time, in respect to that t variable, and that allows us to get to what we want. We just have to solve for some things. Okay, so that's kind of the procedure. It's very open to interpretation, but that's the general way I like to go about it. Okay, so let's do another one. All right, so Yeah, there's a couple of them here. Let's do, I think this one is pretty tough. Let's give this one a go. All right, so this one says a water tank has a shape of an inverted square pyramid. Okay, well, what does that mean? What that means, at least to me, the way I interpret it is we have like some pyramid and it's something like this. It has a square base, right? So something like this. So that's what I think of a square pyramid. Well, what does inverted mean? I think inverted here means it's flipped upside down. So it's going to be, let's see if I can draw this right. So I think it's going to be something like this. Something like that, right? Okay, so square pyramid of length 2 meters. So one of the side lengths here is going to be 2. This is also 2 because it's a square. And we have a height. So that's from this point down. So let me actually change colors for that. So from here down there. So that I'm going to call the height. And I'm also going to call this B for right now because I'm just getting some variables, just like how we did before. Height, they tell us, is 4. Okay. So then they tell us if the water is being drained from the tip, so I presume right here, water's coming out. And they tell us the rate at which it does it. Find the rate at which the depth of the water is decreasing when the water is 1 meter deep. Okay, so that's a lot to take in. Let's start with some variables. So what do we even want to concern ourselves with? Well, we want to concern ourselves with the volume of it. There's going to be some water in this pyramid, it seems, and it's going to be put out of the through the end here. So we are concerned with the amount of water or the volume of the water. We're also going to be concerned with the base and height of it. So if there's water in here, there's some water in here, it's going to take the form of a pyramid, right? It's going to be a smaller pyramid within the pyramid. So it's going to be something like another pyramid right there, like all this. So we'd want to use maybe a formula of volume for a pyramid. So this is another like random bit of trivia, but if you happen to know the volume, you can look this up. I'm pretty sure the volume of a pyramid is 1/3, if at least if it's square on the bottom. It's going to be base squared times height. I'm pretty sure that's the formula. Okay, so now that we have this, we're going to let me select this, bring it down. So I'm going to define V, volume of water in the pyramid. I'm going to let B be the base of the water. So perhaps I'll scratch that out. It's technically going to be that length right there of that red line. That's going to be B, and the height of it, that's technically going to be H. So perhaps that's a better depiction of what's going on. Okay, so B is going to be the base length of water, I'll just say. And H is going to be height of water. So that I think is all the variables we need. Let's now figure out what they're saying. So they tell us that water is being drained at the tip 3 meters cubed per second. So what variable is this associated with? Well, water is always volume, right? You could also think of it as weight, but look at the units here. The units here are meters cubed per second. So we can actually use that to our advantage. Meters cubed is volume. Per second, that makes me think of derivative. And also they say, they say is being drained from the tip at this. They actually don't say rate or anything like they normally do with the derivative, but we can kind of think of it as a rate, right? Because it's being drained from it over a certain amount of time. So I think we can think of that as a derivative, right? So perhaps it's just a guess, but let's give it a go. So dv in respect to time. The reason it's in respect to time is because we can look at this unit right here. It's per second. So that's time, right? Okay. So dv dt is equal to, I'm going to say, 3 meters cubed per second. So you do want to be careful. Technically, there would be a minus here because the volume is decreasing. The volume gets smaller. So actually, I'm going to put a minus right there just so we know that it's decreasing. You can ignore it, but you do want to be careful with that. But regardless, I'll just stick with this convention. Okay, so what other things do they tell us? Find the rate at which the depth of the water is decreasing when the water is 1 meter deep. Okay, so rate at which the depth of the water. So depth of the water means height in our case. So find, this is our goal, find the rate. So that's the rate, like that, right? When water is 1 meter deep. So again, deepness here means height. So when h is equal to 1 meter. Okay, so that's what we want to do. We can actually treat this as given information. We could kind of move this over here if we wanted with our information. So this is kind of the information they give us. It's a horrible M. All right, so now let's run through this. We have our expression. We need to introduce a time variable, specifically derivative. So let's take the derivative of this expression. So, but look at this. We have two variables, b and h. That's going to be difficult to work with. So we don't know anything about the base. So let's kind of view it like this. So the pyramid is going to be decreasing, water's going out. The base is going to be this length right here. That's the base. All we know is that the rate is going to be decreasing, right? Or rather, the volume is decreasing. And we want to find the height of it, which is this length here. So how do we find the base? This is actually pretty tough. So what we're going to do is look at similar triangles. We have not used the information that the base of the whole pyramid is of length 2 and the height is of length 4. We have not used that yet. Let's try to use it. So similar triangles. This right here is a similar triangle to this whole thing. So we can use that. Remember, similar triangle by definition is that the angles of each thing are precisely the same. And look at it, this will be the same, this will be the same as this one, and this one the same as that one. They're exactly the same, so then that means the side lengths are just shrunken. So let's use that. Then that means the ratio of the side lengths. So this is length B, this is length H. The ratios of these things are the same. The base over 2 is equal to the H over 4. So I'm taking this, divide by that, taking this, divide by that. The ratios of how much they're shrunk is the same since they're similar triangles. And you feel free to go through. I think there may be a chapter earlier in the book which talks about some things like this. It's good to review on these in case your professor gives you related rates problems where you need derivatives, or rather similar triangles. Okay, so now, what do we want to do here? What's our goal? If we can keep everything in respect to h, that would be awesome. The reason why I'm thinking that is because when we take the derivative of this, b is a function of time and h is a function of time. That means then we'll have to take the derivative of b, and that'll be db dt. We don't know what that is. So if we can get this to be a function of h, then we'll be in a better place. So let's figure out what that means. We have this equation now. Let's multiply both sides by 2. So multiply by 2 there, multiply by 2. These cancel. This cancels with that, and we get a 2. So b is equal to h over 2. This is exactly what we want, because then now we have h over 2. We can now change our formula to be 1/3 h over 2 squared h. And now this is much easier to work with. We no longer have b's. So that is another part in these problems. When you have other variables which you don't know how to work with, try to see if you can use some other machinery to get rid of them. In our case, we use similar triangles to get rid of the other variables to get the variable we care about. The variable we care about is h, because we're solving for its derivative. All right, so now let's clean this up a bit. We square both the top and bottom. So 1/3 h squared over 2 squared, which is just 4, right? We can clean this up a bit more. 3 times 4 is 12, right? We can combine these two. That's going to be h to the power of 3. That's perfect. Now we have something a bit easier to work with. We no longer have b's. Now we're going to introduce the derivative. Take the derivative of both sides. So we're going to have dv dt, the derivative of 1/12 h cubed. So we can bring this out, right? We can bring it out front and then just take the derivative of that. So that's going to be, bring down the 3. We can simplify this, right? So this will be a 4. We get this. Perfect. Oh, whoops, I actually forgot a step. So remember, h, we're not differentiating in respect to h, in respect to t, right? H is a function of t, right? Something like that. So then we have to do the chain rule, multiplied by dh dt. Okay, we're almost there. So now we have this expression. We're looking for this. So we have a bunch of unknowns. We want to solve for this, but we don't know this and we don't know this. Let's look at our information. We're given this information. That's perfect. We can plug that in right here, right? We can plug that in right there, and that's a number. Also, we have this. For h, we can plug that in directly. That's perfect. So now let's plug it in. I'm going to change colors and do it right here. So now we have -3 is equal to 1/4 h squared, but that's just 1 squared, dh dt. Let's get rid of everything to the other side. 1, let's just ignore that. It's just a 1, right? Multiply both sides by 4. Cancels with that. We're left with -12 dh dt. Boom, and there we are. All right, so we went through all of that and we finally got our answer. So the reason I did the negative at first, so why did I do that? It's decreasing, so I want to illustrate that decreasing of the volume. And what you should see when going through all of this is that it says the height of the water is decreasing. So then that means this should also be decreasing, and so it has a negative. And that's precisely what we want. So if they're asking if it's decreasing, then what you're going to do is get rid of the negative sign, because they already know it's decreasing, so you can omit it. So dh dt is equal to 12. And the only reason I do that, even though we got rid of the sign, is just so that it makes sense and everything comes out as it should. There we are. And we have units. H is in units of meters. and t's in units of time. So we have meters per second. There we are. There's our answer. Okay, so we're getting a bit short on time. I want to do some implicit differentiation before we go. So let's do maybe one or two of those. So I'm going to clear this work. Okay, let's try this one. All right, so we have y cubed. Y cubed plus 3xy plus x cubed equals 12. We want to find y prime. So the derivative is just like another operation. What you do to one side, you must do to the other. And that's precisely what we've been doing this whole time, just kind of implicitly, no pun intended, is that when we take y equals to, I don't know, whatever it is, maybe it's x squared plus x, we take the derivative of both sides. So we take the derivative just like that. So what we do to the left side, we also do to the right side, and that's why we write it dy dx. So derivative of y is equal to 2x plus 1, right? So we apply it to the left-hand side. Okay, so that's what we're going to be doing here. So let me clear this work. So we take the derivative and then we take the derivative of the other side. It's really important that you do the other side because you will get a different result. Many people will forget about it and just say, oh, well, it's just 12. That's not true. It's 0, right? The derivative of a constant is 0. Now we do the left-hand side. Left-hand side, we break up amongst each individual term. So bring down the 3 first, y squared. But we're not done with that term. We have to do chain rule. dy dx. Since x is a function, or sorry, y is a function of x, we cannot just take the derivative of it and just have nothing. Because when we're doing if we're differentiating something like this, what we're doing is we're doing the outside. So that'd be 2x. Normally that's the answer, right? But technically what we're doing is a chain rule. Dx, or rather, derivative of the inside, which is x. But the derivative of the inside is just 1, right? This cancels to be 1. And there's a rule for that, right? So another way you can interpret this, just kind of a good rule of thumb, is you can, since x is just a variable, it's dx over dx. You can kind of treat this as a whole variable and this as a whole variable. Technically, they're infinitesimals. They're really, really small numbers. But regardless, whatever you have over another thing, they cancel. And so it turns into 1. That's kind of another intuition I like to use when going about this. But anyway, to our point, now we take the derivative of this. We have two functions. We have x times y. Y is a function of x, so we have to use product rule. This will be our first one. This will be our second one. So it'll be 3x dx of y plus the derivative of 3x times y. And we'll get to that in just a moment. For right now, let's finish up the last one. Derivative of x cubed, 3x squared, right? And that's equal to 0 on the right-hand side. Okay, let's get us some more room. Okay, so 3y squared dy dx plus, let's see, what is this? Well, this is just dy dx, right? We can just kind of bring the variable up there. So 3x dy dx. And now the next term, derivative of 3x is just 3. So we have 3y plus 3x squared equals 0. Okay, what's our goal? We have this expression now. What were we trying to do with it? Well, we're trying to find the derivative, right? So we're trying to find dy dx. Okay, so let's isolate it. Just treat it as a whole variable. So this has the term. This also has the term. These do not. Let's get them to the other side. 3y squared dy dx plus 3x dy dx minus 3y minus 3x squared, right? Now we're going to isolate dy dx. We can factor out of both of them. Equals minus 3y minus 3x squared. I'm going to bring this up over here. We're going to divide by this whole thing. Do that to the other side. All right, so then this goes on to the other side. So then these cancel. Dy dx is equal to minus 3y minus 3x squared over 3y squared plus 3x. Okay, we're almost there. Let's clean this up a bit. Let me, I'm going to factor out a couple things. I'm going to factor out that negative on the numerator. I'm just going to put it up front because I think it's a bit nicer. It doesn't really matter though for that one. I'm going to bring out the 3y minus x squared. And I'm going to bring the 3 out down here. Y squared plus x. 3's cancel. And there we are. We get our final answer. Whoops, this should be positive. Y plus x squared over y squared plus x, and then we have minus up front. And there we are. We cannot simplify this any further because they are not the same. They kind of look like they can cancel, but this would need a square here. This would need a square, and maybe this would have to be a 1 or something like that. So we cannot cancel these in any way. But that's our result. You do have to kind of question, like, we have y's in our answer, right? Is that allowed? Depends. So sometimes some professors will ask you to solve for y when you can. In this example, I can't imagine a professor ever asking you in this one, because solving for y in this is really tough. So since it's really tough, I would say no, you don't need to. Similarly in this one, there's no way you can easily get y equals whatever, because that would be horrible. So yeah, I would say keeping the y's where they are is perfectly fine and an acceptable answer. And yeah, so that's about it. Yeah, I hope this review was helpful. I sure hope it's pretty close to your material and what you guys are covering. I presume you guys are covering derivatives and some related rates, but and some implicit differentiation. But yeah, so yeah, I hope you guys' exam goes well. One advice I like to give to people is that try to get yourself in a familiar place. I know a lot of classes are still online, so try to get yourself to a place that's pretty quiet and you're familiar with doing work there. Also, something I like to do is there's a lot of things to memorize for this. For instance, all the derivative rules. There's the quotient rule, product rule, chain rule, etc. Right? A lot of these require a lot of memorization. I know for me, I always forget quotient rule. That's a tough one. And like earlier, trying to remember the derivative of secant is pretty tough. So you do have to memorize these things if you want to be snappy on the exam. So what I like to do is study a lot, and then maybe an hour or a half hour before the exam, just do nothing. Just try to relax so that you don't second guess yourself on the exam. Like, oh, am I remembering the derivative of secant incorrectly? Is it just tangent times like cosecant or something like that? Don't try to mess yourself up on that. Just try to go in blank slate. I know what I know. That's what I like to do. But yeah, maybe you guys will find that useful. But yeah, anyways, I hope you guys have a good day and your exam goes well. Bye.